Then I will say a few words about the development of optical filters and then how that combination is used in modern instruments designing these technologies and what the benefits and applications could be. Because we do not have so much time, I will share two resources in the chat for you to watch another recording and also to read the article that I show here on the screen. There are a lot more details than we have time for today. Yeah, a few words about Delta. Delta is a company that designs and manufactures optical thin film components for OEM customers. So we focus on high quality and high volume. And we have worked with fluorescence applications since the 70s for fluorescence microscopy for companies like Carl Zeiss and Leica. So everything we do has more or less evolved around fluorescence filters, so we know the requirements quite well. We are a Danish company located in Hørsholm, which is close to the capital of Denmark, Copenhagen. And another area we're active in is, apart from homogeneous filters, which we will talk about today, are continuously variable filters. So, of course, you know that fluorescence technology is one of the cornerstone technologies in bioanalysis. It's because it's one of the most sensitive spectroscopic techniques that can be used. And in point measurements enables the identification of molecules. And if you use it in microscopy, you can also see the movement. And if we do time resolved, also the temporal development of biological phenomena. It's used in wide field technology, microscopy and confocal. We have seen examples of that before. It's used in live cell imaging, flow cytometry, and also in clinical testing. So it's well known that fluorophores emit light at one wavelength, typically longer when exposed to light of a typically shorter wavelength. And the fluorophores are designed to bind to different, to typical target molecules, enhancing their emission. And that emission is directly measure for the intensity of the target molecule. One very prominent example is, of course, widely known also in public, the PCR test for COVID detection, where a fluorophore binds to the DNA, and then that DNA is detected using fluorescence technologies. So we have also heard about quenched fluorophores before. So when the fluorophore is free, it typically does not emit any light, and only when it binds to the target molecule, it emits the strong fluorescence when it's excited by the correct wavelength. There are basically two configurations how fluorescence instrumentation is used. The most simple one is a 90-degree configuration, where we have a broadband light source, an excitation filter to filter out the correct spectrum for the excitation. We have the sample that is illuminated, and we have an emission filter that is meant to pick up only the fluorescence signal on the photodetector. The 90-degree configuration is chosen to emit the direct light from the source that could reach the detector. In fluorescence microscopy, you typically have a 45-degree reflective configuration, where you again have the light source and the filter. And in between the excitation arm and the emission arm, we have a dichroic mirror at 45-degree angle of incidence that reflects the excitation light and transmits the emission light. It's also possible to arrange all these components in one cube that you typically have in fluorescence microscope to make the handling and alignment of the components a lot easier than if they were separated. So why do people think about multi-wavelength approaches? What are the advantages not looking at fluorescence microscopy with only one wavelength? So when you have multiple wavelengths available in your instruments, you can identify different target molecules simultaneously. You can do multiplex detection of molecules, and as such, then analyze more complex biological systems. And of course, then if you can do that simultaneously, it reduces the experiment time. And for immunofluorescence arrays, you can detect multiple proteins or structures in your assay. And it also makes it much easier to probe dynamical processes and functional interactions. And for that, you need a light source that can emit different wavelengths and multi-bandpass excitation and multi-bandpass emission filters. But how can that be done? So in traditional multi-wavelength setups, you can, of course, swap the components manually, which is very time consuming and for challenging applications not feasible. What has been done for decades basically is to use manual or motorized filter wheels where you can switch within tens of milliseconds between different filters and where you have a limited number of excitation and emission filters on the filter wheel that are then put into the beam path for the correct fluorophore to be investigated. Another option is to use scanning gradient monochromators. They can be adjusted to any given wavelength. It can be very fast within a few seconds. But of course, with monochromators, you are somewhat limited in the bandwidth that you want to excite the fluorophore with, which might diminish your signal. Another option are continuously variable filters. I mentioned that's another field we're working in for fluorescence microscopy. It's typically used on the excitation side, and that has the advantage that you can independently adjust center wavelength and the bandwidth, which makes it very nicely possible to adjust the signal strength of the fluorophore you're looking at. So LEDs have become one of the preferred light sources for fluorescence imaging or microscopy because 60 years after their invention, they have now become available at very high brightness and at a large range of wavelengths. So you can reach many different fluorophores with the suited LED. And typically, they're also quite narrow band compared to broadband light sources, which also reduces the noise signal. And because you do not need to block so much light in the broad wavelength range, also the requirements on the blocking capabilities of the filter can be a little bit more relaxed. They switch very fast within nanoseconds. So that's, of course, then ideal for multiplexed measurements. And you can also combine them in a compact setup with excitation filters and beam combiners to make a very compact tunable light source. And if you have a multi-bandpass filter, you can use them to switch on and off for multiplex measurements several LEDs sequentially. And also compared to traditional light sources, they're very energy efficient and have a very long operational lifetime. So in parallel, over these decades, also the filter technology evolved considerably. In the, let's say, 60s or earlier, filters were very often made of colored glass or polymers. And then a few decades later, basic interference filters, that's when also Delta started working in that field, were made with thermal evaporation. These were soft coatings. They were not very durable and required sealing. Nowadays, advanced manufacturing has come a long way. Ion-assisted deposition has been also a workhorse for several decades. Then plasma-assisted deposition has become the preferred production technology. And later on, we use, since a few years, magnetron sputtering that makes it possible to really manufacture the most complex multi-bandpass filters that we have seen so far. So with that modern technology, you can customize basically any combination of bands, 4 bands, 5 bands, with very high in-band transmission, very high out-of-band blocking, and very high edge steepness. Here is an example of a recent multi-bandpass filters that we made for fluorescence application. And the curve you see on the screen is a measured curve. So it has, you can see that it now approaches, if you will, almost 100% of transmission in a number of bands. And you can, on the next screen see that also the blocking is what you expect from a very good fluorescence filter, OD6 or even better. And what you can also see that there are very steep edges also in the logarithmic plot where the edges really go down almost in a perpendicular. All these filters nowadays are made on single substrates, so they are very compact, very durable, and they can be customized with modern design technologies and the magnetron sputtering technology to specific fluorophore combinations. To give you an idea how that looks like, not that many years ago, we were impressed when we saw filters with 100 or 200 layers. And with the magnetron sputtering, we have produced what you see on the screen here, more than 300 layers in one side of the substrate. And as customers have become aware of these new possibilities, they were also very quick to require specifications that made it possible, for example, to go up to 500 layers on just one side of a substrate. And of course, if you want to work in microscopy, you not only need the bandpass filter for the excitation and emission channels, you also need the beam splitter that goes along in combination with these two components. And also here you can see what has become possible to do with modern design and production technology. Very high transmission in the pass bands of the beam splitter, very high reflection, and again here very steep edges. And have in mind it's at 45-degree angle of incidence, so there's basically or virtually no polarization splitting visible on the edges of the beam splitter. And also these can be customized for specific fluorophore combinations, and again are single substrate solutions which can be combined to very compact optical setups. And this is how it looks like in principle. You have the combination of LEDs. You switch on the LEDs sequentially and then excite different fluid for every time you switch the LED, and the emission filter, of course, then only transmits the respective emission band of the fluorophore. What is quite nice about that instrument design that has been possible with new LEDs and multi-bandpass filters, it's a no moving parts design. So you have seen all the solutions that are possible before. You always need to move something, either a filter wheel, a grating, or variable filters. And here you can have very robust instruments where no moving parts are necessary. So it's possible to switch between wavelengths very rapidly. As I mentioned, it's no moving parts. It also becomes robust, environmentally stable. All the components, filters and LEDs have very long operational lifetime, so very durable instruments, also reducing cost of ownership. They have low power consumption, so it's now possible to also make portable battery-operated instruments. That's not that relevant for fluorescence microscopy, but for clinical diagnostic tools, that's quite nice to make it more compact than was possible before. So, conclusion of my presentation. We have seen developments of LED and multi-bandpass filter technologies. These two have converged in the past years and now enable really advanced fluorescence instrumentation solutions that can enhance your application in microscopy or diagnosis. It's very versatile, it's very durable, and enabling multiplex detection of any combination of fluorophores, and so enabling real-time biological analysis. And I think that will open up new possibilities in analysis and diagnostics in biology. So thanks for your attention.